morning, everybody. I'm Jonathan. I'm the Senior Applications Engineer for the Systems and Electronics business unit here at Leap. So that actually now covers more than just electronics because of our systems capabilities, and our new embedded software stuff is also included in that. So today I was going to cover, it will be a rough introduction. You could easily spend 2 hours on every single one of these bullet points, but I've got an hour, so I'll do my best. With systems engineering, we introduce a new style of design complicated systems, which I've kind of coined behavioral design, because we tend to stop focusing on lots of the small details and just start optimizing the platform straight away. And that leads straight into stuff like control systems, and I've also got a little bit of information on one of the latest ANSYS developments, which we call the digital twin, and that's good for doing maintenance and studying your virtual prototype once you've constructed it and you're testing it. Then we've got a bit on what I call the low-frequency electromagnetic products, which is mainly focused on electromechanical and power electronics. And we also lead into the final topic, which is high-frequency electromagnetics, and that's things like developing wire harnesses, antenna design placement, and then mitigating issues once you find you've got them. So there's a bit of a paradigm shift to consider once you start including system type simulations. So historically, everyone has worked on a what I'd call a bottom-up approach. So you start with, I need to build a car, therefore I need to build brackets for the engine, therefore I should jump straight into mechanical and start designing those first. This is very difficult once we start scaling it up. So once you have a team of 50 engineers in it, and you need them each to be working as efficiently as possible, in much the same way that we develop software to scale on lots of cores, we need to develop a design process which scales with lots of engineers. So if we start at the top level, so if we wanted to look at a hybrid car, we don't bother looking at how many poles the motor should have, but we work out roughly what voltage it should run on, how much power it needs to have to achieve our acceleration targets, what size the battery needs to be to run. And once we have ballpark figures for each one of those, we can start pushing information down from the top towards the detailed design phase to let everyone get started. The big advantage of ANSYS is because you're within the same product environment for the entire design cycle, you can iterate through. So if you start with a system level model, you design one component in detail, so let's say you do the aerodynamics of the car, you can extract the information from that model very, very quickly, load it back into the systems tool, and run the scenarios again. So as each team iterates and produces more and more information about your design, this virtual prototype system becomes more and more accurate. And so this, in terms of coupling capabilities together, we have full support for all the mechanics and fluids products. Our electromagnetic products have been integrated for a long time as well. The new integration is embedded software. So if you have a large team developing safety critical code, so it's the stabilization system for cars, it's the autopilot of aircraft, being able to test that software realistically is much, much easier if you can plug it into a virtual prototype, which includes a lot of. So the downside of system engineering is it needs to be fast. If we use 3D finite element models, fluid dynamics, electromagnetics, it's almost always slow or painfully slow for detailed models. So for example, quite often it might take, for 1 second of real world time, it takes 10 hours of computational time. And that's just ridiculous. You can't do a low scenario type work with computation that's that slow. So we need to get at least 1,000 times faster before we can do useful scenario type simulations. So if you want to do an entire flight cycle, if you want to fly a UAV for a meaningful length of time, say an hour, and look at power usage and the different ways to follow paths and tracks like that, taking 1 second for 10 hours of computation is just unfeasible. So with our current tools, we've developed a lot of techniques for integrating all the physics together without having those massive slowdowns. So at the moment, we're working at about 1 million times faster. So we've done realistic work where it took us 3 weeks to run the 3D model, and it takes us less than half a second to run the systems one. So we've actually beaten, I think the fastest we've ever seen was about 10 million times faster. So because we're now simulating so quickly, we can now realistically optimize a lot of transient style scenarios that we couldn't before. Like you can actually let the person drive the car. So we have a lot of, I guess I'd call them cheats. They're actually just really clever maths. So the way you start off with systems engineering is, Simplora is a model-based systems engineering tool. So if I go and add laser pointer, you usually start off with libraries. So we don't bother putting a huge amount of detail into the model. You know, it can be a motor, it can take some voltage, some current, convert it into some output torque, and then you can go and add transmissions to it, you know, aerodynamic loading, everything's at a very simplified level and it runs very, very quickly. A very big advantage of this technique is we still maintain parametric workflows like we do with the rest of our tools. So if you wanted to go through and start sweeping through different combinations, it's not always trivial whether reducing the weight of the battery by 5% is enough that we can sacrifice, you know, 5% of the output power of the motor and gain a net advantage. So you have the freedom to use the shotgun approach. You can just run thousands and thousands of different scenarios without really having to deal with any significant simulation time. And by the end, you plot them all on one big graph, you click the one you like, and that's where you're starting to narrow down your possible design development pathways. So that's your first cycle. From then on, you now have access to the rest of the ANSYS portfolio. So you start doing detailed aerodynamic work, you start doing detailed electromagnetics, mechanical, etc. Then you develop these detailed models, which you can go and manufacture. And when you're done, there are export buttons in almost all the products, which allow you to drag and drop what we call a reduced oil model back into the model you constructed before. So now the model runs about 10 times slower. It's still about a second. But you have all the detail that you've just made from doing your detailed design work. And so while all this is going on, usually the mechanicals and electricals clump together during design work and the softwares are left out. In this case, there's no need to leave them out. So because they have access to this model, the system that you're working on, they can start plugging their software in, and while they're developing, their model gets progressively more and more accurate. So it's in terms of, I guess you call it parallelization of the design process. All of a sudden, your engineering teams can get much, much larger without incurring these massive penalties of waiting for other teams to finish their own part. With the latest release of ANSYS, we've also added support for what is called the functional mock-up interface. So particularly for the automotive industry, there are a lot of tools for modeling things like tire wear, which you can plug into Simplora, almost like a USB port for simulation. And that allows you to use all the complex modeling that someone else has done and build it straight into your ANSYS model to keep improving the accuracy. Next slide, hopefully. That being said, we now move on to a real benefit of having these virtual prototypes which run fast, and that's that we can now start to review the entire system with very, very high precision. So it's quite feasible to look at nanosecond level precision over a runtime of an hour without incurring too many penalties. So for control systems like PID, you know, it's not usually too much of a big deal to tune the system. You've only got 3 constants to dial in. There's reasonably prescribed ways of achieving this. But where it gets a lot more complicated is when we start doing state, space, and multiple out type control systems where the factors are never really that independent of each other. If you change the gain of one area very slightly, you don't change the delay time in another, you often lead to a completely unstable system. So you now have the option to optimize automatically. It runs fast enough that if we run the extra 10 iterations, it doesn't really have that much of an effect on us. So now the only real thing we have left on our Christmas wish list is if only ANSYS could write all the code for our controller at the same time as building all these virtual prototypes. It turns out Christmas comes early this year. So the ANSYS SCADE product, which you would come across, it's probably of particular interest to the UAV group because it's certified for aerospace use, but there's a lot of use in the automotive industry as well. is that we implement the same sort of design flow we've just been using for mechanical and electrical, but we do it for software. So we start off with a system-level architecture plot. We check that all the signal flows through are sensible and that we never cross paths and variables don't get used twice. We can then go click one more button and we start doing logical-based design. But instead of writing code this time, we use flowchart type methods and state machines. This means that we can mathematically check every single possible scenario very quickly, and we guarantee to produce error-free code every single time, obviously assuming your flowchart is correct. So then once you get to the end of that, once you've proven your flowchart works and is mathematically accurate, then you click one more button and SCADE will either produce C code, which you can go and compile straight in your controller, or it produces ADA code if you have any work with that. Obviously C is a lot more common, but it's nice to have the functionality there as well. So we're going to look at a couple of examples. The best way to see something in action is to show you lots of examples. This is an application where we used a wireless charger for a car, but we found that we hit thermal constraints every single time we iterated through the design process. So this bottom part here is the wireless base plate. So this sits on the floor of the garage. It's plugged into mains. It can supply a large amount of power, and it wirelessly transfers it to this top coil here, which would be mounted at the bottom of an electric car. So we also have air blowing through the heatsink below it, and we need to try and maintain this and keep it cool. So we don't have any control over the environment whatsoever. So you could buy this product, whether it's part of a Tesla or something else, and you could own it in Saudi Arabia, where the ambient air temperature is in the 40s, or you could buy it in Sweden, and the ambient air temperature is below zero somewhere. So we always have to guarantee that no matter what, if you put your hand on this device, that you're never going to get burnt. It can be uncomfortably hot, but we must never burn it anyway. So we have two design options for this system. We can either be really, really conservative, so you can choose to look at the worst case scenario. If it's a 40-degree ambient air temperature, what's the maximum power we can dissipate through the heatsink? Or we can add a couple of sensors and we can use the control software to regulate the charge rate and make sure we never exceed those temperature limits. So the first stage is to build up the model. We built magnetics models first, and then we did CFD on them. So moving down, this is what a system in Simplora looks like. So this block here is the raw CFD model. We have a number of inputs. The first is the heat density, so the amount of power that we're feeding into a coil. We have options here to change the ambient. So at the moment, they're all set to an ambient of 25. And then this model calculates in real time what the temperature of the coil is, what the temperature of the enclosure is, and how hot the exhaust temperature is. So these numbers are fed around this loop here, and we end up back in the selection stage. So we can set different targets depending on the particular temperature we're measuring. So for example, the coil temperature limit is 90 degrees Celsius, because at that stage the plastic starts to become malleable and we start to damage the device. The outside temperature of the enclosure is about 65. We judge this to be safe enough that you can put your hand on it and not be burnt too quickly. And we have an exhaust temperature limit which is slightly higher because we don't anticipate you sticking your fingers in through the exhaust of the fan. So each of these are separate, and we only have one PID controller here. So we've obviously tuned this PID controller to react at an appropriate speed to the system. And then we have the state machine here, which cycles through showing which of these is the high priority we want to look at. So for example, if we're closest to the coil limit of 90 degrees, then this is the difference that we want to look at to control the system. If we're closer to any other two, we want to swap. So if we move on and see what the result of this looks like, this blue line moving up here is the fixed input. So if we are really conservative and we work on a worst case scenario, we set a fixed charging rate and we end up charging in about 54 hours. If we are allowed to adapt the control power. So if we're allowed to increase it when we're a long way below the temperature limit and then regulate it back once we get there, then we gain a huge amount due to the initial thermal inertia of the plastic. And so we end up shaving off 16% of the charge time. So in hotter climates, the improvement will be even larger. In colder climates, it'll be less of an advantage, but we still guarantee safety, and that's usually enough to save a lot in development time. I have another example, and this is looking at ABS braking of a car. So this is another safety critical system. You might be noticing a pattern now that a lot of the things we do are safety critical. We always have to adapt to the environment. So if we're braking on slick roads, if there's ice, if the car is twisting, we need to adapt for all these different scenarios. Now, the benchmark we're going to set is that we're going to look at the same system, but without the controller intervention, so basically flicking off the ABS system. But we want this to be expandable in future. So currently we're just looking at ABS. Things like car stability, coring assist, things like that would be future applications, and we want the system to be expandable to include those. So in this case, the system's more complicated. So what we've done is we've created subsystems. So if you double-clicked on each of these blocks, the Simplora, it would open up the subsystem, and you can change the topology. And we've also broken up the system based on the physics it's working in. So we have a battery model here, which is based on our electrochemistry designs. We have some power electronics, which drives our electromechanics, which includes things like our valves and solenoids. Then we have this pneumatic hydraulic braking system, which actually includes the model of the car as well. So we have these two inputs, the main one here being the pedals, and these are driven by realistic waveforms. And because our ABS system runs all the time, it has its own complete independent loop. So we feed in the amount of slip at the wheel, the speed the car is traveling at, and then this feeds out a specified current value, which is fed with the power electronics. So if we zoom in on just the mechanical subsystems, then we have, here we go. This is part of what we call a Medallica programming language. So Simplora has adapted over the years to include as many different options for people to model it as possible, because everyone has their own preferred. For doing mechanical and hydraulic systems, Medallica is our preferred choice. If you Google Modelon, they have a particularly nice website. So we go and add a number of inputs to this and a number of outputs. And then within each of these, we have their own subsystem. And so you can add as much or as little detail as you like, but they're always lumped. So here we have a diaphragm spring here. It's just this one element. We have some extra mass attached to that. We have some more custom models for things like reaction disks. And then we have some valves as well. So adding one more expands the hydraulic system. So because, if you remember, we looked at reducer modeling at one stage, where you've taken a detailed electromagnetic or mechanical system, and you convert it into something simple. This is what the design process looks like for a solenoid coupled to a valve. So this is our Maxwell model. We did it in 2D axisymmetric. We ran a transient simulation to characterize how it would respond. We then pushed the export button, and we get this extra block here. So it has our two input terminals. It has a reference point for one end of the arm, which is at the bottom, and then the amount of applied force is X to the top. So this is a full nonlinear system. Usually developing reducer model this takes a long time. Because the process is automated, it's very convenient and just about anyone can do it. So then we choose not to model things like the stops and the springs explicitly mechanical. We add them on as these extra lumped blocks. And then this feeds out to the amount of force and travel on our valve. So we end up looking at a lot of plots like this in systems where we want to look at different values of variables, and we always want to look at them in the time scale. So here is where the driver takes his foot off the accelerator pedal and slams it onto the brake. So it takes him about half a second to achieve all of that. So then the vehicle's speed immediately starts to reduce. So if we move down, we can see there's a lot of slip happening. So it completely locked up the wheels, and the car is now sliding. And then these plots at the bottom show that the ABS is not functioning. It's just sitting there, not doing any intervention. So we want to slow down from 15 meters per second down to 0. And so we achieve 0 at just over the 2.25 second mark here. Now, if we compare it with ABS, the driver's reaction time is exactly the same. The difference being now that the brake pressure here starts to become regulated by those control valves and the control software. So whereas the slip before hit minus 100, now we're regulating down to sort of minus 6, minus 8. And this is the current being applied to our valve and our force that the valve is exerting, from the solenoid is exerting on the valve. So you can see it quickly switching it on and off here to regulate it. This is what I call bang-bang control. We could definitely make this a bit more sophisticated in the future, but it's a good first pass. So if we compare the speed of the two overlaid on the same plot, this initial stage is simply the driver putting his foot on the accelerator bit on the brake pedal. And once he's slowed slightly and now the vehicle's locked up, the ABS starts to kick in and we start making our net gain. So without ABS here, we track down to about 2.25 seconds. With the ABS, because we've regulated the amount of slip to be the absolute maximum braking force, we can apply at that wheel contact patch. And we shave up about 1.6 meters, and it takes about 0.25 of a second less to stop. So I imagine this is actually probably on a nice hard surface. If we added variable surfaces into the design, so you can change each of the wheels' friction characteristics, then things like black ice are going to make this system a lot more advantageous to the driver as well. So unfortunately, I would spend a couple of hours there showing you various different examples, but I've got a short list of some of the things I thought of that might be directly applicable to hybrids, particularly whether it's UAVs or cars. So we have a lot of capabilities when it comes to battery simulation, particularly lithium-ion, although we are doing lead-acid work at the moment as well. We can look at all the way down to the electrode level. So if you want to study the different ways that the electrodes interact, you can do that in our fluids packages. Then we have workflows to help you take the information and jump through each of the levels. So the next stage up would be electrical and thermal simulation for a single cell. That includes particularly cooling for lithium ions in cars. It's a very big topic at the moment. You can look at how a cell, a module, or a pack is going to charge and discharge, particularly when you're looking at things like regenerative braking. This is quite important. And another big topic is parasitic modeling. So the amount of copper required to get electrical energy out from every single electrode to the two main connectors at the end of the battery is a very large web of various different conductors weaving through all the cells. So there's a not insignificant amount of resistance and capacitance and inductance associated with that web. And so you can choose to optimize that as an extra feature at the same time that you're working to optimize the chemical kinetics and the thermals of the battery. So this is where the Ansys Workbench platform comes in handy. If you load all those simulations in, set particular outputs you're looking at, and start to optimize, then you can look at the interactions and behaviors of all the variables all at once. Inverter and motor drive simulations is probably actually the first application that Simplora was used for. So modeling the losses within your semiconductors, so where it's more likely to be IGBTs, but could be MOSFETs, is very, very complicated. And so we have the ability to scan one of your data sheets, and you choose which graphs are relevant, particularly if it's in German. Then Simplora will go through and build that semiconductor model for you. And then from then on, it's in your library. You can just copy and paste it in. And it also comes with temperature dependence. So at a later state, if you decide to work at a different operating temperature, all the models in Simplora will automatically shift their characteristic curves to the new operating point. All this work tends to lead to EMI. For university level teams, this tends not to be a big problem. but for industry level, the Volkswagens and Audis of the world, EMI is a massive consideration for how their car operates. So this list, I've noticed, when I was writing yesterday, is almost dominated by electrical and electronic type products. So that's where Simplora grew out of. The latest big push has been incorporating the fluids packages, and more importantly, the rigid body dynamics from the mechanical products. So we've actually started to do more and more robotics work with Simplora. And so you can take the models you produce in mechanical and expose pins on each of the joints so that you can work on control systems for those mechanical rigid body type applications. So I mentioned at the start that I was going to explain how a digital twin works. So the basic premise is you do a lot of work initially in Simplora and mechanical and the rest of the ANSYS suite to explore your design to find exactly the right dimensions, sizes, and materials to produce the perfect turbofan engine or whatever. Then you go through and you build a full digital prototype, you design the engine management system for it, you tune the fuel burn rate, you look at vibration, all these different core design type applications. But you get to the end and now you've produced this amazing model and you archive it and stick it somewhere and no one looks at it again. ANSYS thought up the idea with GM that what if we could go and take that model you've just made, make sure it runs reasonably quickly, and we're going to embed it in a new GUI. And so then when you are looking at this product operating in the real world, you can feed data from real world sensors into this digital twin model, and ANSYS will compare the two. So if your turbofan engine fuel inlet pressure is slightly off, the digital twin will flag it. It will then start pulling in more sensor data. Is there too much vibration? Am I looking at a fuel burn rate which is too high? Am I outside thermal parameters? And it starts flagging things for you to go and check out. Depending on how complicated digital twin is, it can do things like fatigue calculations. So it will throw a red flag if the vibration is causing your design life of your bearings to drop too far. And so particularly for automotive models now, where the design isn't actually too complicated, this is very, very useful for looking at a system which you can't actually touch. So if it's mid-race or a UAV is in mid-flight, you can pull up your digital twin and use it to start checking whether what it's doing is sensible, where you need to do service. So that concludes the systems side of this. If you have questions, feel free to click the email or chat message, and I can explain things in more detail. Moving on to, I guess, the more detailed design side of electromagnetics products. Our low-frequency products are focused on electromechanical devices for the most part. So things like permanent magnet motors, induction motors, solenoids, loudspeakers. Eddy current braking was a big thing for the Hyperloop not that long ago. And then transformers, inductors, and bus bars and the power distribution side of your networks. So we tend to split them into two different types of design work. So the first is, I guess, what I call static or pseudo-static design. These tend to be designs which don't move, and they don't experience really extreme operating conditions. So we can make good approximations by simplifying the analysis down a bit. So for automotive and UAVs, this tends to be the area where we're always trying to minimize weight, but not increase losses too much. So for example, if you could shave 150 grams out of your power supply design, that leaves you 150 grams for something else, or you just leave it out completely and take the free performance gain. You can also look at things like bus bars. If you choose to use a hollow core rather than a solid core, and you're running at frequency, then you can make a net weight savings with virtually no loss because the current is flowing on the outside of that conductor rather than through the middle. Particularly for battery designs, voltage isolation becomes a problem. You're running a 480 volt battery pack, and you don't use the right amount of plastic to shield the high voltage conductors from each other. you tend to have breakover, the battery fails, and then you have the same problem that Samsung had with their the latest Note device, which spontaneously caught fire. The last thing we tend to do, which probably isn't very applicable to this application, but is very much a problem if you're someone like Infineon, and that's you want to minimize the losses from getting from the middle of your semiconductor device out to the connections to the outside world. So this also applies to PCB designs. If you're designing your own PCB and power supply to fit together as tightly as possible, you tend to have tracks which can be longer than they need to be. So using these types of tools, you can optimize your track links to make sure that all of your semiconductors are balanced when they're under full load. So now we move on to the more exciting part. Transient type designs tend to be things like motors and transformers and solenoids, and these are where we make the biggest gains in the drivetrain of a vehicle. So if we can successfully drop the volume of magnets in a motor without negatively affecting it, then we can improve performance actually significantly. But now if the rotor's on the outside of the stator, or else we tend to focus on things like reducing the cost of the motor, so we can produce more of them more cheaply. Minimizing the amount of soft magnetic materials in the motor, so if you can reduce the core or the sheathing, then you can save a lot in losses. And so this is where you can make big gains in efficiency with motor design. The last thing, which is very much a priority for UAVs and hybrid vehicles, is maximizing the power density of an electric motor. So if we can get twice the power out of the same volume or half the volume for the same power, that frees up an enormous number of different applications to make gains in other places. So if you can add more cells to your battery, if you can save weight somewhere, you can make much, much bigger gains simply by tweaking that one small area. And if you know that in advance, so if you've done a system simulation and you know that, if I can just save a little bit on my motor, then I can make gains in the other regions, you can give each design team their own targets in order to prioritize that one variable, which will cascade down the line. The last application tends to be more a verification type piece of work, but motors can quite often operate in non-ideal scenarios. So while the motor operates just fine on a bench in 20 degrees ambient, if you jam it all together with power supplies and batteries and its core temperature gets elevated, then you can start to damage things like the magnets within the motors. So by coupling Maxwell with ANSYS Mechanical, you can do a lot of these verification activities fully automatically within Workbench, including things like vibration. That way you know whether you can sacrifice some mounting hardware to save a bit more weight. So this is an example of where we took a permanent magnet motor. In this case, we're looking at a fixed inner stator, a rotating rotor on the outside. We can change basically anything about this motor, but we have a very fine balance between all of our priorities and how we want to achieve them. And to be honest, it's usually the opinion of the motor designer as to how we balance things out. So if we can sacrifice a little bit of weight of these magnets, that reduces the weight of the rotor by a significant amount, and because this is the part which is spinning, therefore we reduce rotational inertia, efficiency goes up, and overall the motor is a lot better. So the goals of this optimization is we want to maximize torque, we want to maximize efficiency, but we want to minimize the torque ripple, because that applies dynamic loading to the rest of the downstream powertrain. So this is what the variables we have access to when we design this motor. We're able to tweak the magnet to be closer in the middle than at the outsides. We can shave off the corners. We can tweak the widths of these gaps between the stator poles. And we also have the ability to tweak a few of these inner parts of the rotor to save soft magnetic material. So this is how we characterize each design iteration and what we look for. So we have torque. Obviously, I guess we figure it's the average roughly of this plot here. We have losses, which are calculated independently using the integration tools. We define efficiency as electrical energy input divided by the mechanical energy output. There's lots of different ways to calculate this number, but we're going to use this one in this case. And then we have this concrete way of defining what we call torque ripple. So I can look at the plot and say, oh, well, there's a ripple and that's torque ripple there, but because our frequency content can change, we need to work out a way to prioritize exactly what we call a good torque ripple and what we call bad torque ripple. So in this case, we're going to choose the sum of amplitudes. So we run a fast Fourier transform across the waveform. We ignore the 0th term, and then we just integrate under the plot in order to gain a fixed, hard, concrete value for what our torque ripple is. So we're actually going to use the new Optimisation optimization tools. It's produced by a company called Donato, who's now an ANSYS partner. And what that will do is you feed a set of variables into Optimisation, and Optimisation will work out the minimum number of solutions it needs to run in order to cover the entire design space as efficiently as possible. So in this case, it came up with this plot of the output efficiency on this vertical axis and the output torque of the motor on the horizontal. And there's a distinct curve that it follows with a very nice fit of 0.955, which shows us that we should, in theory, be able to tune our motor anywhere along this curve to suit the application. So if we look at the original on the black line here, and then we look at our optimized value here, we've chosen to sacrifice a little bit of torque here, and a little bit of electric power, and a little bit of output mechanical power as well. But our losses have dropped dramatically, so they've been cut in half. And our efficiency has actually gained a bit of a boost. So if we then look at the geometry it created, so on the left is the original, sharp corners, and an even coverage. The new one has actually carved out a small bit of the magnet here and shaved off the corner. And also thickened the outside of the rotor as well, which has saved us a lot of money. So potentially you could do another optimization process and change the outer diameter to improve the rotational inertia further. But for the most part, this has gained us our maximum efficiency by optimizing very small changes in the tooth width. I had to measure with a ruler, it's small. The main difference is the shape of this outer magnet on the rotor here. So that was kind of a quick overview of what we use for the low frequency tools. I'm going to have an equally quick overview of the high frequency ones. So particularly in the last 2 or 3 years, cars, particularly in the automotive industry, UAVs have always been like this, so it's nothing new, is the ability to add a huge amount of communication between the vehicle and the outside world. So this picture here is a radar cruise control. So this looks distinctly like an Audi. And so there is a small radiating antenna array down the bottom of the grille, and that measures the distance to the car in front. Then we've got a lot of other things, like, for example, we want the ability to have autonomous cars, and so therefore we need some way of transmitting information from the roading network and the cars around it to the car in order for it to keep track of where it is, and avoid things like if there is roadworks ahead, then the car will need to reroute some routes automatically. This will, because it adds so many antennas and radiating features to the car now, all the cars will be a lot more susceptible to outside interference. So this is both for things like hacking or alternatively just for poorly designed electronics, which can interfere with operations. So if you chose to broadcast an antenna somewhere in the vicinity of 60 gigahertz and a car is driving along with its radar cruise control turned on, all of a sudden you've effectively blinded that system. So not only does the car need to know what to do about it, in order to protect the occupants, it could also jump channels and start looking for a cleaner frequency band to work with. So it's all about maintaining the safety of the car and then prioritizing performance second. So PCB wiring harnesses always cause a lot of problems because we're trying to transmit a large amount of power at the same time as we're producing these very, very fine data signals. And so when you're designing a cable loom, some of the ANSYS tools are available that you can look at the way you've laid it out, which conductors are closest to which other ones, and it will predict where you're likely to see interference. Particularly for new cars, we have a very, very large number of wires. This starts to become a very, very large problem. But particularly for things like motorbike engines, where the cable loom tends to be very dense and all in one area, this is a very useful tool for solving those intermittent problems, which are always very difficult to diagnose. Antenna design is kind of bread and butter of the ANSYS electronics tools, particularly when we're looking at radiation patterns and where the potential places that we can place an antenna around. So obviously the antenna needs to work in all scenarios, but other than that, it doesn't really care where it's placed. We have the ability to calculate the radiation pattern from the car. So you load in the car geometry, put your antenna design somewhere, and then look at how it leaves the car. It gives us the extra option to start coupling some of the products together. So for example, if we take the ANSYS Electronics desktop and we couple it with the CFD, the most common application for this most people jump to is thermal design. But in this case, what we could do is we could specify that the radiation efficiency shouldn't drop below a certain point, but at the same time, we want to minimize the amount of aerodynamic drag induced by adding that antenna to the car. So if you're able to change the covering dome of that antenna, then our workbench interface can look at both designs, start tweaking, and make sure that we achieve minimum drag while still achieving the radiation efficiency that we require. So a lot of these alternative designs that you can possibly do. As a side note, that technique was used to optimize stealth bombers. So they want to look at the radar cross-section and they link it through to the shapes of the air intakes for the engines. So in order to optimize aerodynamic efficiency and minimize the radar cross-section at the same time. So this is a huge problem for the UAV industry when you start having lots and lots of these different antennas placed on the same device. So if you have an IFF tag, it's a military drone. If you have a standard control radio system, if you have a data uplink, GPS, all these antennas have to work on the same platform and not interfere with each other. So in much the same way that we use Simplora, we have a separate tool for doing interference called EMIT. And you can drag and drop on your different radios from the pre-configured library and connect them to antennas and start to look at different cases where you might end up transmitting on the same channel. So for example, if the IFF system is transmitting very strongly on a very similar channel to the VHF or the GPS, then you could end up with a couple of extra spurious harmonic frequencies jumping through a couple of different other systems and ending up saturating the IFF receiver. And then, of course, the UAV gets shot down. So it's quite an important topic to deal with, particularly in aerospace. The same techniques apply to automotive. You can, if you have multiple antennas and systems broadcasting simultaneously, then you can do the same sorts of checks for cars as well. So as an example, when you're driving down the motorway next time and you hear a beep, this is the system that's being solved. So on the motorway overbridge, there tends to be a little transmit-receive antenna, and then as each of the cars go under it, it tries to transmit a signal to a little tag in front of this car, which is that little donut shape you can see. And so in this case, we want to check that we always have a strong signal to each of the cars, even if you have something like this large semi going past, which starts obscuring some of the road and reflecting energy back. This is more, I managed to find this really interesting example from an unnamed car company, which means it's probably Volkswagen. This is a PCB which is there for controlling solenoids in the suspension. And so when initially did the design work, they found this one particular electrical conductor through the middle here was susceptible to outside interference. But it wasn't too bad, and it was good enough to pass the first time through. Once they added this extra wiring harness, so in particular this one conductor here, all of a sudden they found that this wire basically became an antenna and was very, very susceptible to receiving outside interference. And so it turns out that this is the reason why. So if we look at the waveform along the top, initially, we have a bit of interference on it from external sources, but it's more than enough to maintain this nice bathtub curve and only get one error every 1e to the 16 bits, which is basically never receiving an error. As soon as we had that wiring harness on, then it receives much, much more strongly. The bit stream is basically unreadable, and our error rate drops by 14 orders of magnitude, increases by 14 orders of magnitude, and basically becomes a whitewash. So in this case, the mitigation steps are, if we go back to the picture, we need to either shield this trace through here, or we need to ground it properly. Unfortunately for us, it doesn't specify exactly how they did it, but that's probably the reason why. So that's kind of all the material I have. I realized it was a fast overview of a lot of products all at once. So there are quite a few tutorials on the leaderboard that they're not included in this week's tutorial material for all three of our electronics products, so PCBs, low frequency, high frequency. And then we're increasing the systems area all the time as we gain more and more materials. So if you have a particular application in systems that you'd like to look at, you don't quite know how to fit into the product and which products you can couple together, you definitely get in touch and we can help you out with that. Other than that, I think I'm going to say thank you very much for listening, and I'll pass it back to Scott.
Thanks very much, Jonathan. Cheers.